Hello friends, this video is brought to you by www.moeteaching.com.
Before stating the theorem formally, let us understand that when we talk of natural numbers, they can be prime and composite. Now the question arises, can all the composite numbers be produced by multiplying two or more prime numbers? To find the answer to this question, let us take some large composite number. Say we take 32760. And now find the factors of this number. We know the prime factorization technique. We start with 2. On division we get. Again this can be factorized further. Again with 2 we can get 4095. This goes with 3 and gives 1365. Continue in this manner. Keep dividing with prime numbers till we get 1. Now 32760 can be written as the product of its prime factors. That means 2 to the power of 3 multiply by 3 to the power of 2 multiply by 5 multiply by 7 multiply by 13. So we can see that we had taken a composite number at random and we could write it as the product of prime numbers. We can repeat this with several other composite numbers and see that they can be written as the product of prime numbers. Hence we reach a conclusion that every composite number can be written as the product of power of primes. Now we are in a position to state Fundamental Theorem of Arithmetic, which says that every composite number can be expressed or basically factorized as a product of primes. And this factorization is unique, apart from the order in which the prime factor occurs. Apart from the order in which prime factor occurs means, suppose I am factorizing 12. I can start with 2, or I can start with 3. Whichever way I do, 12 is equal to 2 square into 3. So the order in which the prime factor occurs can be different, but the factorization is unique. In other words, we can say that given a composite number, there is one and only one way to write it as a product of primes, as long as we are not particular about the order in which the primes occur. Let us sum up the whole result in general. Given a composite number x, we can factorize it as, then x can be written as product of prime numbers p1, p2, p3 and so on, if we assume that these prime numbers are written in ascending order, that means then the prime factorization of x is unique, and if we combine the same primes, we will get the powers of primes. For example, if we prime factorize 32760 and arrange them in ascending order, we get this combination. Now if we combine the same primes, that means if we combine 2's, we get the powers of primes. So if we combine 2's, we get 2 cube. If we combine 3's, we get 3 square. There is only 1 5, 1 7 and 1 13. So here we must notice that once we have decided that the order will be ascending, then the ways the number is factorized is unique. Let us read the question. Consider the number 4 power n, where n is a natural number. Check whether there is any value of n for which 4 power n ends with the digit 0. To prove this, we will use Fundamental Theorem of Arithmetic. First of all, we can see that 4 is not a prime number. So 4 power n cannot be a prime number, and we reach the conclusion that 4 power n is a composite number. We are asked to check whether there is any value of n for which 4 power n ends with the digit 0. If 4 power n were to end with the digit 0 for some value of n, then it would be divisible by 5. That would mean that prime factorization of 4 power n would have 5 as one of its factor. So let us try to factorize 4 power n. This can be written as 2 square whole power n, which is same as 2 to the power of 2n. That means its prime factorization is 2 into 2 into 2 and so on 2n times. So the only prime in the factorization of 4 power n is 2. But the Fundamental Theorem of Arithmetic states that every composite number can be expressed as product of primes, and this factorization is unique. That means there is no other way in which 4 power n can be factorized. So 5 cannot be the prime factor of 4 power n for any value of n, and hence there is no natural number n for which 4 power n ends with the digit 0. Let us revise highest common factors and lowest common multiples. Let us first look at factors and multiples. When a number divides another number exactly, then the divisor is called the factor of the dividend, and the dividend is called the multiple of the divisor. For instance, if we divide 14 by 7, we see that it is completely divisible by 7 as it is leaving the remainder 0. Then we can say 7 is a factor of 14 and 14 is a multiple of 7. We start with definition of highest common factors. Highest common factor is the greatest number which divides two or more numbers without leaving a remainder. We now proceed to various methods of finding HCF of two or more numbers. First method of finding HCF is by finding the common factors. Let us proceed and understand with an example. Suppose we have to find the HCF of 15 and 20. First we find the factors of 15. We start with 1. 1 into 15 will give us 15. 2 is not a factor of 15. 3 into 5 is 15. 4 is not a factor. Again 5 into 3 is 15. So the factors have started repeating and we stop at this stage. Similarly, let us find the factors of 20. 1 into 20 will be 20. 2 into 10 will be 20. 3 is not a factor of 20, but 4 into 5 will give us 20. 5 into 4 gives us 20. So now the factors have started repeating and we stop here. That means 1, 3, 5 and 15 are the factors of 15, while 1, 2, 4, 5, 10 and 20 are the factors of 20. Now let us look at the common factors. 1 is a common factor and 5 is a common factor of 15 and 20. Out of 1 and 5, 5 is the highest common factor. So we can say that HCF of 15 and 20 is 5. Let us look at another example. Say we have to find HCF of 16, 48 and 80. We start with finding the factors of each of these. After writing down all the factors of the three numbers, let us mark the common factors. 1 is common to all of them. 2 is common factor. 4 is a common factor. 8 is a common factor. And 16 is also a common factor. So we find that 1, 2, 4, 8 and 16 are the common factors of 16, 48 and 80. Out of these, 16 is the highest. So HCF of 16, 48 and 80 is 16. Although this method of finding HCF is very easy, but it is very cumbersome. So let us look at more methods of finding HCF. Another method of finding the HCF is prime factorization method. Now suppose we have to find HCF of 36, 44 and 60. What we will do is, we will prime factorize each of these. Now 36 can be written as 2 into 2 into 3 into 3. Similarly, 44 can be written as 2 into 2 into 11, and 60 can be written as 2 into 2 into 3 into 5. Next we mark the prime factor that appears in all the three numbers, and then HCF will be given by product of common prime factors, that is 2 into 2, which is equal to 4. We can see that finding HCF by finding the factors of numbers or by prime factorization method is very cumbersome. So we introduce another method called successive division method. Alternatively, we can say that HCF is the product of the smallest power of each common prime factor in the given numbers. Let us see how. We write each number in exponential form of the prime factors. So 36 is 2 square into 3 square. 44 is 2 square into 11 power 1. And 60 is 2 square into 3 power 1 into 5 power 1. Here we can see the only common prime factor is 2, and the smallest power of 2 in the three numbers is 2 power 2. So the HCF will be 2 square, which is equal to 4. Let us discuss successive division method. Suppose we have to find HCF of 36 and 90. Divide the bigger number, that is 90, by the smaller number, which is 36. On dividing, we get the remainder 18. Now divide the first divisor by the first remainder. On division, we get the remainder as 0. So the divisor is the HCF of 36 and 90. We will say that HCF of 36 and 90 is 18. Let us take another example. Suppose we have to find the HCF of 185, 407 and 333. Then also we can use long division method. We first start by finding the HCF of 185 and 407. Let us divide. On division we get remainder as 37. Now divide 185 by 37. We can see that remainder comes 0. So 37 is the HCF of 185 and 407. Now find HCF of 37 and the third number. Again, follow the same procedure till we get remainder 0. Here we can see that it is completely divisible and we are getting remainder 0. So whatever HCF we get here is the HCF of the three numbers. In this example, the HCF is 37. Lowest common multiple, or the LCM, is the smallest number which is divisible by each of the given numbers. Let us now recall LCM. We start with the method of finding the multiples. Say we have to find LCM of 6 and 15. We first find the multiples of 6 and multiples of 15. Multiples of 6 will be 6, 6 into 2, 12, 6 into 3, 18, 6 into 4, 24, 6 into 5, 30, 6 into 6, 36, 42, 48, 54, 60, and so on. Let us find the multiples of 15. 15 into 1, 15. 15 into 2, 30. 15 into 3, 45. 15 into 4, 60. 15 into 5, 75, and so on. Now the common multiples are 30, 60, and likewise we can get many more common multiples. Now out of the possible common multiples, 30 is the lowest of them. So LCM of 6 and 15 will be 30. Another method of finding LCM is by prime factorization method. Say we have to find the LCM of 8, 24 and 36. Firstly, we will prime factorize each of these numbers. Then 8 can be written as 2 into 2 into 2. Similarly, 24 can be written as multiple of its prime factors, and 36 also can be written as multiple of its prime factors. Now ring all the common factors. 2 is a common factor. Again 2 is a common factor. Again 2 is a common factor for 8 and 24. 3 is a common factor for 24 and 36. Now take only one factor out of a set of common factors. From these we take 2. This set we take 2. This set we take 2. This set we take 3. And multiply with the non-common factors. We get the LCM to be 72. So for LCM we are taking only one factor out of the set of common factors and also multiplying with the leftover prime factors. Alternatively, we can say that LCM is the product of the greatest power of each prime factor involved in the numbers. Let us see how it works. We can write 8 as 2 cube, 24 as 2 cube into 3 power 1 and 36 as 2 square into 3 square. Now the prime factors involved in these three numbers are 2 and 3. We have to take the product of the greatest power of each prime factor. So the greatest power of the prime factor 2 involved in the three numbers 8, 24 and 36 is 2 to the power of 3, and we have to take the product with greatest power of next prime factor, that is 3 square. This also gives us LCM 72. Another method of finding the LCM is called the division method of LCM. Say we have to find LCM of 72, 96 and 160. Write the numbers as shown. Divide all numbers by a prime number which divides at least two of the numbers. Here, for instance, prime number 2 can divide all three of them. So, we get 36, 48 and 80. Write the quotient in each case below, which we have done. If a number cannot be divided exactly, write the number as it is in the next row. That means if any of these numbers could not be divided, we would have copied it like that only. Now, keep dividing by prime numbers until the last row has co-prime numbers with no common factors. In this case, we can again divide by 2 and get 18, 24 and 40. Again it can be 2 to get 9, 12 and 20. We can again take 2. Now 9 cannot be divided, so 9 can be written as it is. Then 6 and 10. If we take 2 again, then we write 9 as it is, 3 and 5. Now we can take 3, we get 3, 1. Now 5 cannot be divided, so 5 as it is. So we have reached numbers which are co-primes, that is, they do not have common factors. Now multiply all divisors and all numbers left in the last row. The product will give us the LCM of the given numbers. So we have 2 into 2 into 2 into 2 into 2 into 3 into the digits left in the last line, 3 into 5. This will give us LCM to be 1440. There is an interesting property connecting the HCF and LCM of two numbers. The property says that product of two numbers is equal to the product of their HCF and LCM. Note that we are talking about two numbers only. Let us take an example and verify. Say we take the two numbers 6 and 8. Then product of 6 and 8 is 48. Now let us find the HCF of 6 and 8. Say we use the long division method. So here the HCF is 2 let us find the LCM. So LCM will be 2 into 2 into 3 into 2, that is equal to 24. Let us find the product of HCF into LCM. Which is equal to 2 into 24, which is also 48. So we can say that 6 into 8 is equal to 48, which is equal to product of their LCM into HCF. That is, we have proved that first number into second number is equal to HCF of the numbers into LCM of the numbers. Let us also state the relation between HCF and LCM of three numbers, say P, Q and R are the positive integers. Then LCM of P, Q and R is equal to P into Q into R into HCF of PQR whole divided by HCF of PQ multiplied by HCF of Q and R multiplied by HCF of P and R. Similarly, HCF of P, Q and R will be given by P multiplied by Q multiplied by R into LCM of P, Q and R whole divided by LCM of PQ into LCM of Q and R into LCM of P and R.